Welcome back to the deep dive. Today, we are grabbing a stack of sources focused on, well, an industrial necessity that probably doesn't get a lot of attention, the simple fan.
Right.
Except, when that fan has to work in a place that could literally explode, then it stops being simple.
Definitely not simple then.
It becomes really an engineering marvel.
Absolutely.
Our sources today focus on hazardous location blowers. Specifically, we're looking at some high-performance Ramfan models available through PE Energy Industrial Supplies. And our mission really is to understand why this specialized ventilation is maybe the most critical safety component in these volatile environments. We need to figure out what makes these units so different from, standard industrial equipment and why getting them certified is just completely non-negotiable.
Yeah, absolutely critical.
So this deep dive is for you, the learner. If you need to quickly get your head around the vital role this gear plays in places you might never actually go into. Think refineries, chemical plants, underground mines, oil and gas facilities.
Yeah, places where the air itself can be a hazard.
Exactly.
So maybe first things first, we should define what we mean by a hazardous location, because it's way beyond just a dusty workshop or a damp area.
Right.
We're talking about atmospheres where you have enough flammable gases or maybe ignitable dust or volatile vapors hanging around that there's a real risk of explosion.
Okay.
So these ventilation systems, they aren't just moving air around. They're specifically engineered to operate safely inside those explosive conditions.
Meaning the fan itself can't become the problem.
Exactly. Its very presence can't add to the hazard.
Yeah.
Our sources, they talk about using them for things like tank cleaning, purging pipelines, keeping conditions safe during maintenance or construction in these really high-risk spots.
Because if you just brought in a regular shop fan.
Oh, disaster potential. A standard motor, even a tiny spark that's not contained, that could ignite the whole area. It's immediate, potentially catastrophic.
Okay, that really sets the stakes. So let's unpack the why. Why is moving the air so important that the equipment doing the moving has to be explosion-proof? What's the core job here?
Well, the number one job is safety, achieved through controlling the environment. And crucially, it has to be continuous. It's what we'd call an intrinsically safe approach.
Intrinsically safe. Okay.
So these blowers, they need to run constantly circulating air for basically two main reasons.
Right.
First, they're clearing out harmful contaminants. Could be heavy vapor settling low down or fine dust that's explosive when it's suspended in the air. They basically dilute the atmosphere, keeping it below what's called the lower explosive limit.
Makes sense. And the second reason?
That's about oxygen levels, especially vital in confined spaces. Think about workers doing maintenance inside a tank or a narrow shaft.
Yeah, you can't breathe in there without help.
Exactly. Ventilation isn't just nice to have, it's a literally life support. It stops asphyxiation and it prevents that buildup of an explosive atmosphere. The source material really hammers this home. These blowers are built for continuous operation, uninterrupted. They're the lifeline, making sure that workspace stays non-volatile.
Okay, that's a huge difference, isn't it? Between just standard air movement in a factory and this continuous, life-critical environmental control.
Totally different worlds.
They're not just cooling things down, they're actively managing this invisible, potentially lethal risk.
Precisely.
All right, now for the really interesting part, I think, the engineering. How on earth do you design an electrical device, a motor spinning a fan blade, and guarantee it won't be the thing that sets it all off?
Yeah, that's the challenge.
What are the specific safety features built in? What makes it explosion-proof?
That is the core engineering problem, right? It's way beyond just making it tough. It's about active prevention and also passive containment. You know, the fire triangle, fuel, oxygen, ignition source?
Yeah.
Well, in these places, the fuel is there, the oxygen is there. So the fan's entire design has to focus on eliminating that third element, the ignition source.
Okay, how?
Let's start with sparks and heat. These blowers use things like explosion-proof housings. Now, the idea isn't necessarily that an internal spark or failure can never happen. But if it does happen inside the motor casing, that housing is built strong enough, often heavy-duty cast aluminum, maybe specialized steel, to completely contain the force and the heat. It basically smothers any internal ignition event before it can escape and ignite the dangerous atmosphere outside.
So the super tough casing is like the last resort, the containment strategy.
Exactly. Containment is the last line of defense. The first line is preventing the spark or excessive heat in the first place.
How do they manage that?
Through really carefully sealed electrical components, for one, plus things like motor overload protection and specific design choices to manage heat buildup. Think about it. A high-speed motor, if it's not sealed perfectly, can generate friction, heat, potential sparks. So these specialized blowers use extremely robust bearings, really tight sealing, just to minimize friction and ensure the motor never gets hotter than a specific safe temperature limit for the particular gases or dusts it's rated for.
Okay, that makes sense. I also saw mentions in the sources of something called a flame arrestor. How does that fit in?
Ah, the flame arrestor. That's a clever bit of passive safety tech. It's crucial, especially if the blower is hooked up to ductwork.
Okay.
Imagine you've got this hazardous atmosphere, right?
Mm.
And for some reason, a flame starts traveling inside the ducting like a mini explosion moving along the pipe.
Yeah.
The flame arrestor works by quenching that flame. It's usually made of layers of metal mesh or plates with very narrow channels or holes. As the flame front tries to push through these tiny gaps, the metal surfaces absorb the heat incredibly quickly.
Ah, like a heat sink?
Exactly. It cools the flame so fast that it drops below its ignition temperature. It hits the quenching distance, and it just dies out. It can't get through the arrestor to ignite the bigger atmosphere on the other side.
Wow. That's smart engineering. Okay, so we have the tech, the physical design. But you mentioned earlier it's useless without the paperwork. Certification.
Absolutely fundamental.
Yeah.
You can't talk safety in explosive atmospheres without talking certification. It's the bedrock.
So what are the main ones we need to know about?
We're primarily looking at global standards like ATEX and IECEx.
ATEX.
That's the European Union directive. It stands for Atmospheres Explosibles.
Okay, and IECEx.
That's the International Electrotechnical Commission system. It's a global framework for certifying equipment used in explosive atmospheres.
And these are tough tests, presumably.
Oh, incredibly rigorous. They cover everything. Material strength, how the unit handles heat, the quality of the electrical sealing, impact resistance, you name it. If a blower fails these tests, it simply cannot legally be used in a designated hazardous location, period.
And in North America? Is it just...
In North America, you'll often see the UL Mark Underwriters Laboratories. That confirms it meets the regional safety standards, which are often aligned with IECEx principles.
Yeah.
These certifications are what guarantee that, say, a specific Ramfan model is actually suitable for the zone it's going into, whether that's a Class I zone for gases and vapors or Class II for combustible dusts.
Gotcha. And just to give the learner a feel for the scale, these aren't all massive units, are they? The power varies quite a bit.
Oh, a huge range.
Right.
Because ventilating a small manhole is totally different from clearing fumes in a giant storage tank.
Right.
Our sources mention everything from really compact, portable 8-inch models, like the UV20 Max X series you mentioned. They run on maybe a third of a horsepower. Perfect for spot ventilation. Then you scale up, you get into the mid-range 12-inch models like the EFI 75XX, maybe 3/4 of a horsepower.
And then the big ones.
Yeah, the 16-inch industrial units, the EFI 50, EFI 120, EFI 150 series. Those can go from half horsepower right up to 1.5 horsepower.
Wow.
And that jump in horsepower directly translates to how much air they can move and how fast. Cubic feet per minute, or CFM, that determines how quickly you can make a large, dangerous space safe to enter.
Okay, that really paints a picture of the engineering side. Now, let's pivot a bit. From the tech itself to the business of safety actually getting hold of this vital certified equipment through the right channels, like PE Energy. We saw in the sources that the rules around buying this stuff, the compliance and financial protocols, seem incredibly strict.
They absolutely have to be, because buying this equipment isn't like ordering, paper clips. The purchase process itself is tied into the whole compliance chain.
How so?
Well, the most critical thing from a logistics standpoint is getting the product identity right. Customers must provide the correct OEM part number.
OEM, original equipment manufacturer.
Right. For a certified blower, that specific part number is the link. It guarantees they're getting the exact unit that matches their safety assessment, their regulatory needs, maybe existing certifications for their site.
No substitutions allowed.
Definitely not for the core certified unit. Now, PE Energy might offer high-quality aftermarket replacement parts for non-critical components, like maybe filters or handles, and they'll specify that. But the blower itself has to be the precise OEM certified model.
Okay. And what about the money side? Why have the tight security on payments, the credit card caps, the wire transfers?
Yeah, things with a credit card limit, often around $5,000, and requiring wire transfers for big international orders, that's mostly down to the high value of the equipment, its specialized nature, and frankly, global regulations around shipping high-value industrial goods.
Oh.
Plus, you generally can't place these orders over the phone. Why? Because you need a clear, documented, traceable audit trail for purchasing certified safety equipment. It protects both the buyer and the seller.
Got it. And the freight forwarder thing for international orders over $2,500.
That's not just about getting it shipped. A good freight forwarder handles the complex customs paperwork. They help prove that this certified, potentially sensitive equipment is being transported and imported legally, meeting all the regulations. It's all part of managing the risk associated with explosion-proof gear from start to finish.
So even the buying process reflects the high stakes involved. It's not just admin, it's part of the safety documentation trail.
Precisely.
All right, let's move into the field then. The equipment's arrived, it's properly certified, it gets installed, often in some pretty tough, remote, hazardous spot. How does the team actually use it day to day? And maybe more importantly, how do they maintain it so that certification stays valid?
Maintenance is absolutely key. It's the difference between having a certified safety device and, well, a potential ignition source sitting right there.
So installation first. Is it always fixed in place?
It can be flexible. Many models are pretty weather resistant, so they can handle controlled outdoor use, not just indoors. You can get permanent mounting kits, wall, ceiling. But often, especially for confined space entry work, they're used as temporary portable units.
Okay. And using them, is it just on or off?
Often more sophisticated than that. Many models have variable speed settings and adjustable louvers or directional controls.
Why is variable speed important? Wouldn't you always want maximum airflow?
Not necessarily. Sometimes blasting air too fast in a dusty environment can actually make things worse by stirring up a combustible dust cloud. So operators need that fine control. To gently sweep out vapors or dilute contaminants without creating a secondary hazard, precision matters.
Okay. Now, the crucial maintenance part. What happens if that gets skipped? If someone forgets to change a filter, for instance, does it just not work as well, or does it actually become unsafe?
It actively compromises safety. Neglecting maintenance, especially cleaning or replacing integrated filters, is a major risk. If a filter gets clogged, the motor has to work much harder to pull air through. It starts to overheat. If that motor gets hotter than its certified operating temperature, that T rating linked to its ATEX or UL certification, then boom, it's effectively lost its certification. It is no longer guaranteed to be explosion-proof.
Wow. Okay. So filter changes are serious business.
Absolutely.
Yeah.
Regular maintenance isn't just about filters, though. The schedule may be every few months, maybe more often, depending on how dirty the environment is. Always check the manual. It also includes inspecting the protective housing.
Looking for damage.
Exactly. Any significant crack, any deep corrosion on that explosion-proof casing means its ability to contain an internal event is compromised. That unit has to be taken out of service immediately for repair or replacement.
So the physical integrity is just as important as the internal workings.
They work together. And interestingly, these units are generally engineered to be pretty energy efficient, high airflow for minimal power draw. But again, that efficiency completely depends on keeping them clean and well maintained.
Okay, so let's try and wrap this up. What does this all mean for you, the learner? We started in these really dangerous, potentially explosive environments. We traced the path through some seriously specialized engineering, talked about the vital global certifications, the strict buying process, and the absolute necessity of maintenance. These hazardous location blowers, they're clearly not just fancy industrial fans, are they?
Not at all.
They're purpose-built safety systems, engineered, tested, certified to provide continuous, reliable, and crucially, non-igniting air movement in places that demand absolute perfection.
Yeah, you could call them the quiet guardians of industrial safety, always there doing a critical job.
Yeah.
But, the next step in safety often involves moving beyond just reliable physical operation
What do you mean?
towards digital awareness.
Sure.
Our sources mention that some advanced models can now integrate with central control systems, often called BMS, building management systems.
Okay.
So if you connect these blowers into the BMS, you suddenly open up possibilities for remote monitoring, remote control, tracking their performance in real time.
I see where you're going with this.
Think about it. If the whole point is maintaining safe air quality and preventing explosions, what new level of safety assurance, what new level of, say, regulatory compliance do you unlock when you can monitor critical data airflow rates, motor temperature, maybe even filter condition remotely, continuously?
Instead of just relying on periodic checks?
Exactly. So this raises a really interesting question, I think, about the future. About the convergence of industrial safety systems and the IIoT, the Industrial Internet of Things.
That is an intriguing thought. Taking safety management from a scheduled reactive process to something potentially continuous, data-driven, maybe even predictive.
Could be a game changer.
That level of real-time environmental insight could fundamentally alter how industrial risk is assessed and managed around the world. definitely something to mull over.
Mm.
Well, thank you for diving deep into the essential world of explosion-proof ventilation with us today, the learner. Maybe go explore how continuous digital monitoring is starting to reshape compliance and safety in your own field. We'll see you next time on The Deep Dive.